Hi YouTube, Mr. Lim here again, and this is our video on buffers in acids and bases. So let's get started. Alright, so this is what we're going to be learning about. Okay, so let's go through. So let's just have a look at this text. So when a weak acid is present in a solution that has a high concentration of acid molecules and a low concentration of hydronium ions, okay, in a dynamic equilibrium state. So what does that mean? So let's take an example like ethanoic acid, so CH3COOH, okay. When that's present in solution, there is a high concentration of acid molecules because, you know, this thing will ionize with water, all right, and form CH3CO minus and H3O plus. Okay, but you need to remember that because it's a weak acid, there will be a high concentration of this, and there'll be a low concentration of these two things here. Okay, so high concentration and low concentration of both of those two things. Okay, because it only partially ionizes. All right, so lots of those ethanoic acid molecules. Okay, so we're calling them acid molecules, and a low concentration of the hydronium ions. So this low concentration of hydronium ions means that the pH of the system does not indicate the concentration of an acid very well. And when I say acid, I mean acid molecules, okay? Because you can have a ton of these, but your pH won't really show that you have a ton of these because it's only showing this concentration here. Right? It will reflect the low concentration of hydronium ions, okay? So low concentration of hydronium ions. So when you add hydroxide ions then, okay, it's going to drop them into the system. What are they most likely to collide with first? They're most likely to collide with the acid molecules than they are with a hydronium molecule or ion. Okay, well, they're going to collide with waters lots, but they're going to generally collide with this one before they collide with this one. And you'll notice that because it's a hydroxide ion, it has the ability to react with both of them. It has the ability to react with this acid molecule. It has the ability to react with that hydronium ion. Okay, so the options are it crashes into a acid or ethanoic acid molecule and turns into water and ethanoate ion, or it crashes into a hydronium ion and just turns into water. All right, but because this one here, the acid is at a high concentration and the hydronium at a low concentration, this one is going to occur much more. Okay, so when the hydroxide ions are added, they will react with the acid molecules. This reduces the change in concentration of hydroxide ions. So if you were to add 100 of these hydroxide ions, now because you've reacted with some of that ethanoic acid molecule, right? Now the 100 that you added is no longer 100, maybe there's only 10 left or something like that. Okay, and thus it limits the change in the pH that occurs because any additional OH minus is going to affect the concentration of H plus and therefore affect the pH. But because you've removed some of them by reacting with the acid, it's not going to change as much. It's still going to increase, but just not as much as there would have been if you had put it into some neutral water. Okay, so there'll be a little change, just not a lot of change. Okay, so idea is that you got a weak acid, high concentrations of acid molecules, low concentrations of hydronium ions. Okay, so when you add a base to it, it has an option to react with those two, right? And it's going to react generally with these ones first because there's going to be so many more of them, and so therefore it's going to react with that and form that, and therefore reduce the change in concentration of that OH minus, and therefore reduce the change in concentration of pH. So this all occurs again oppositely if you have a weak base. Okay, so if you have a weak base and you add hydronium ions to it. So if you start off with a weak base, so something like NH3, okay, this is a weak base, and then you see it's, what's the G? Let's move this across a bit. Right, its reaction with water. Okay, it's going to make ammonium ions and OH minus. Okay, again, you're going to have a high concentration of weak base, right, and a low concentration of ammonium ions and hydroxide ions. So that when you add hydronium ions to it, or just any acid to it, right, for hydronium ions are going to react with the high concentration of NH3 compared to the low concentration of OH minus. So if I were to add some H3O plus, it would rather react with the NH3 because they're much more common to form NH4 plus and H2O, compared to it crashing into a low concentration OH minus to form some water. Okay, so high concentration of, oops, not that one, high concentration of this one and a low concentration of this one means that this one here will occur much more. Okay, the reaction with the base molecule. It's going to react with the base molecule. Okay, so again, it goes through that, reduces the change in concentration of hydronium ions, which limits the change of pH. So if you added in 100 of these H3O pluses, some of them would react and then go away, and therefore there would be a small change in the pH. Okay, again, it would still decrease this time, not increase, but not as much as if you had added it into neutral water. Okay, so that's the idea when you add something to a system with a weak base or a weak acid. So then, what do you do? Perhaps maybe then if I put together some conjugate base of a weak acid. So if you, considering the conjugate base of a weak acid is itself a weak base, okay? So what that's saying is that the conjugate base of a weak acid, so here's a weak acid, CH3COOH, its conjugate base, which is CH3COO minus, this itself is a weak base, right? So if you have the conjugate base of a weak acid and the weak acid, so you want a beaker full of both CH3COOH and CH3COO minus, it has the ability to perform reactions with either hydronium or hydroxide ions. Okay, when you add hydronium, the acid reaction, it's going to react with the base. If you add hydroxide ions, it's going to react with the acid molecule. Okay, so chemists can take advantage of this and create solutions that can oppose or limit the change in pH when small amounts of acid or base are added to it. These solutions are called buffers. Okay, in this part here, small amounts of acid is kind of key because you can't add a ton of acid or base to it and still expect it to buffer. All right, so that's the idea. If you have both these two things here, a weak acid and its conjugate base, or a weak base and its conjugate acid, in the same solution, they will be able to react with either hydronium or hydroxide ions and consume them when they're added to limit the change in pH. Okay, so if a solution of a weak acid and its conjugate base is created with high concentrations of both the weak acid and conjugate base, it can oppose additions of acid or base and keep the pH of a solution relatively constant until the concentration of appropriate ions runs out. And we'll go through that in a diagram in a moment. The amount of acid or base in a solution that can resist is called its buffering capacity. So let's go through this idea. Okay, so we just said something along the lines of, it's got to have CH3COOH, a weak acid, and its conjugate base, CH3COO minus. Okay, so remember that these things here, the acid will react with water to form CH3COO minus and H3O plus. Okay, but we know that this has a high concentration here and a low concentration of that and a low concentration of that. Okay, but if you were to add a ton of CH3COO minus ions as well, this would also react and form this. OH minus. Okay, so you can make a solution with a high concentration of that as well. All you would need to do is, just add in, what are we going to do? How are we going to do this? We can add in some CH3COOH, that's easy enough to find, and you can add in some sodium ethanoate, and you would have high concentrations of both CH3COOH and CH3COO minus. Okay, so you'd have high concentrations of both of those. So once you have high concentrations of both of those, I'm going to represent this diagrammatically over time. Okay, so you have your CH3COOH and your CH3COO minus. And I'm going to put in H3O plus over here in small concentrations because, there's not going to be lots of it in the solution. All right. So if I was to add some H3O plus, okay, so this is starting to look like an equilibrium graph because it is, right? This is concentration, this is time. Okay, if I add some H3O plus, that H3O plus, it's going to react with which one of these two? Is it going to react with the acid or the base? Well, because you've added an acid, it's going to react with the base. Okay, so this H3O plus reacts with this here in this following formula. H3O plus CH3COO minus to form CH3COOH and H2O. And that particular reaction here will cause the reduction in the concentration of that H3O plus. It will also cause the reduction in the concentration of CH3COO minus by, a 1-to-1 ratio, right? And if you really want to know, it will also produce some CH3COOH as well, right? So that's what will happen if you add an H3O plus. But what's the key here is that the change here is relatively small, okay? That change in H3O plus over here is relatively small. And if you have a relatively small change in H3O plus, you're going to have a relatively small change in concentration or change in pH, okay? So you could continue adding H3O plus, and it would continue to go down as this gets consumed, okay? And if you added some more, it would continue to go up and then a little bit down. And you'll notice that, there's a little bit of change every single time, all right? And you could continue to do this until you'll notice that, first of all, but now there is a significant amount of change in here. But what happens here, right? At some point in time, this thing's going to run out. You're going to run out of CH3COOH. CH3COO minus. And then when you add in some H3O plus, it can no longer react with anything because there's no CH3COO minus there. And so therefore, it's just going to stay at that level, okay? It's not going to go back down after the initial spike. It's just going to stay at that level, okay? And so now you have this big old change in pH compared to what was initially very small changes in, well, not that one, small changes in pH, right? So that's the idea, or when you add an acid to it, and it would be the opposite when you add a base to it. The CH3COOH would go down, and the other one would go up. And this one would, well, go down because you're adding base to it, all right? But that's the idea. Now, the idea of buffering capacity is effectively, if you have a high concentration of this blue CH3COO minus, at some point it runs out. So all of those bits that you've added before it runs out, probably not that one actually, right, before it runs out is the buffering capacity, okay? All of these ones here combined, that's the buffering capacity, because you've effectively added acid, added acid, added acid, added acid, until it runs out of the ability to buffer anymore, right? And so all of those combined is the buffering capacity, okay? And if you were to have this concentration even higher at the beginning, you would have an even higher buffering capacity, okay? So key ideas are the buffering capacity is dependent on the, the weak acid and its conjugate base being relatively high concentrations. When you add an acid or a base, it will react with the relevant thing here. So the acid will react with the base, and the base, if you added a hydroxide, it would react with the acid. That concentration changes a bit, and then it goes back down, and then there's only a minimal change overall, which results in a minimal change in pH. Okay? So let's have a look. What's next? So to make a buffer, you need to have high and preferably equal concentrations of weak acids and conjugate bases. And so that's what we said before, high concentrations of weak acids and their conjugate bases, or vice versa. That way, when you add acid or base, the pH change will be counteracted by a substance in the solution. So whether you add acid or base, something's going to react with it. All right? How do you make that? Okay, you take a weak acid and you add the salt of its conjugate base, and then you have a solution with high concentrations of each. Okay, so here we go. That's what it says. Add a solution acid and its conjugate base. Remember to state the name of the salt of the conjugate base. So you can't just say I'm adding in ethanoate ions. You've got to add in some sort of sodium ethanoate or potassium ethanoate, because you can't add ions by themselves. Okay, so add to a solution of acid, like ethanoic acid, its conjugate base, right? The various pairings just have to be some sort of acid-base combination, right? So in terms of H3PO4, okay, if you were to add in sodium dihydrogen phosphate, which is its direct conjugate base, right, its first conjugate base, it would work as a buffer, kind of, but you should remember that this is acidic, but this is also acidic, so not really that helpful, okay? So both of those things are acidic, okay? So it would be very poor at buffering acids, right? Because there's no base real form to think, because this as a form is not really basic. So better to add in H3PO4 and some sodium phosphate, because here is your acid molecule form and here is your base molecule form, right? Or ion form in this case, right? So you would add those two things to make a buffer solution. Remember, why would this not be a very good buffer? Because this ain't a weak acid, all right? You need to find weak acids to make buffer solutions, okay? Carbonic acid and sodium carbonate, another option, okay? And if you want to go with a base, NH3, and perhaps some ammonium chloride, okay? All you need is some sort of acid form and some sort of base form, okay, of the same thing. All right, so to make a buffer, you could also 2A weak acid or base, add a small amount of strong base or acid to lower the concentration of the weak acid and increase the concentration of the conjugate base or thing. Okay, so what does that mean? Let's go through the idea. All right, let's say that you have some ethanoic acid and we know that it has a high concentration. When you add a bit of I'm going to add a bit of base to it, all right, some sodium hydroxide, okay, the reaction is going to occur to form, what am I forming? CH3COO minus plus H2O. Okay, so say you started out with 100, or let's go 1,000 of those. And then because, this is a weak acid, weak acid, there's only going to be, you know, like 30 of these. Okay, so we haven't got high and equal concentrations of the acid and the base. But when I add in the base, and maybe I only add in a small amount, 400 or so, okay, these 400 OH minuses are going to react with the, what are they going to react with? They're going to react with the ethanoic acid molecules, and they're going to reduce its concentration. So now instead of it being at 1000, it's only going to be at 600. And in the process, it's also going to produce 400 of these CH3COO minuses. Okay, so now you have a roughly, not really exactly, but roughly equal and reasonably high concentration of both the acid and the base molecule. Okay, but this is only when, look here, when you're adding a small amount of acid or base to a highly concentrated weak acid or base. Okay, small amount of strong acid or base to a highly concentrated weak acid or base to bring this concentration down to something like this and bring this concentration up to something like this, and so they're roughly equal-ish. Okay, that's that idea. Okay. So we have a look at these exam questions, and if you don't want to have a look at these and don't have time, you can look at these later. But here are some exam questions about thingies. All right, so let's have a look. Explain how the HPO4 2- and H2PO4 prevented any significant pH changes when the SO2 was bubbled into solution. So prevented any significant pH changes, you're considering buffers. You should be able to see that this is the acid version and this is the base version. So even though it's not a weak acid and base pairing, it has some sort of form of acid and base pair within that solution. All right, the SO2, and if we remember from our acids, non-metal oxides are acidic, right? SO2 will actually react with water to form H2SO3, which is acidic, sulfurous acid, right? So here's the ideas that you want it to answer. Okay, so number one, SO2 forms H plus ions. Okay, that's what we're talking about. The SO2 produces acids. This is a buffer, just ideas that why does it prevent any significant pH change? Because it's a buffer, right? The additional H plus reacts with the base form in the buffer, right? It consumes the majority of the added H plus, not all of it, the majority, and therefore there's a minimal change to concentration of H plus, and that will result in a minimal change to pH. Okay, so those are the ideas that we went through. Let's have a look at this another question. Okay, benzoic acid, right? This is a titration curves. You haven't done titrations yet, but the idea is that where, okay, so the question is, define the term buffering and explain why it occurs during this titration in the region that you circled in part B, which you should have circled around that there, right? And use an equation to support your answer. Okay, so buffering is a solution which resists changes in pH. So look here, you added some sodium hydroxide, and the pH did not rapidly rise. It did not rapidly rise like that. Okay, instead, it stayed relatively constant, because remember, you can't get rid of all of it, you can get rid of most of it. All right, let's have a look at what the answer key said. So, buffering is the ability to resist significant changes to pH when small quantities of acids and bases are added to it. This is something that is very key to add to your answers, that it can only be a small quantity of acids and bases, because if you don't write that, you lose the mark. All right, so small quantities of acids and bases. Buffering occurs in this region because you've got the acid form and the base form present. Okay, and you'll learn more about this when we do titrations. You have some equations on how they react with the different things, right? In this buffering region, there's no significant or dramatic increase in the pH because the added hydroxide ions are consumed by the benzoic acid. That's the acid molecule, okay, the acid molecule there. right? So those are the kind of ideas. That's all we got time for. Adios.